The rapid advancement of artificial intelligence compels us to consider profound philosophical questions. Specifically, we must examine the epistemology of AI. How do machine learning systems acquire, represent, and validate what we might call knowledge? This inquiry delves into the very foundations of AI's cognitive processes. Unlike human cognition, AI knowing is fundamentally statistical and pattern-based. Machine learning models, particularly deep neural networks, learn by identifying complex correlations within vast datasets. This process involves adjusting internal parameters to minimize prediction errors, effectively encoding patterns without explicit symbolic understanding. Their knowledge is thus emergent from data, not from pre-programmed rules or innate concepts. It is a form of inductive inference, where general principles are derived from specific observations. This contrasts sharply with traditional symbolic AI, which relied on explicit, human-defined knowledge bases. The system's understanding is a reflection of the statistical regularities it has observed. The representation of knowledge in AI systems is largely implicit and distributed. In neural networks, knowledge is encoded across millions of weighted connections and biases. These numerical values collectively represent the learned patterns and relationships. This distributed representation makes it challenging to pinpoint specific facts within the system. While some models use symbolic representations or knowledge graphs, the dominant paradigm of deep learning relies on these opaque, subsymbolic encodings. The internal state of a trained network is a complex, high-dimensional mapping of input to output. This contrasts with human knowledge, which often involves explicit concepts and propositions. The justification of AI's knowledge presents a significant epistemological challenge. For many complex AI systems, particularly deep learning models, the reasoning behind a particular output is not directly inspectable. This black box problem hinders our ability to understand why a system arrived at a specific conclusion. Efforts in explainable AI, or XAI, aim to provide insights into these internal processes. Techniques like saliency maps or feature attribution attempt to highlight which parts of the input most influenced an output. However, these explanations are often post hoc approximations, not direct articulations of the system's internal logic. The justification of AI knowledge often relies on empirical performance and robustness testing. If a system consistently performs well on unseen data and is resilient to perturbations, its knowledge is deemed reliable for practical purposes. Yet, this pragmatic justification differs from the human demand for logical coherence or causal understanding. The epistemology of AI forces us to reconsider our definitions of knowledge, understanding, and justification. AI systems operate on principles distinct from human cognition, offering a new lens through which to view intelligence itself. As AI becomes more integrated into critical domains, understanding its unique epistemological foundations will be paramount. Further research must bridge the gap between statistical learning and human interpretable knowledge. This ongoing philosophical and technical inquiry will shape our relationship with intelligent machines.